Welcome to the exam walkthrough for the GCSE Physics Higher paper. The first thing to do is write your name. Okay, so this paper starts with a question about wind farms. So it says, Figure 1 shows a large wind farm off the coast of UK. Now we've got about 13 wind farms off the coast of UK. Offshore wind farms are from the coast out at sea. The nearest one we have is Barrow-in-Furness, and then there's another one in Liverpool, both of which have about 30 wind turbines each. It says the mean power output of the wind farm is 696 megawatts. Now, the units immediately should strike you and go, well, it should be in watts. And it says it's enough for 580,000 homes. And then the question is, calculate the mean power needed for just one home. Your answer has to be in watts. Because the question gives the power output in megawatts, the first thing to do is convert 696 megawatts into watts. Mega stands for 1 million. So to get from megawatts to watts, I need to times by 1 million. That is 1,000. When you do that, it ends up being 696,000,000 watts. That actually earns you 1 mark. The next mark comes from doing the actual calculation. For one home, you have to do 696 million divided by 580,000. That's exactly what I'm going to put into my calculator. 696,000,000 divided by 580,000 gives me an answer of 1200 watts. And the second mark actually comes from writing 1200 here. Remember, all questions should be answered in that space. So all of this working out should be right here. Okay, next question. It says on one day the demand for electricity in the UK was 34,000 megawatts. Suggests 2 reasons why the wind power was not able to meet this demand. Well, let's go back to how wind power works. Even though it's always windy in the UK, it's never enough wind to power all the wind turbines. So the first answer that you have to write is wind is unreliable. You can't count on it to be windy, so it may not be windy that day. The next reason that you have to go through is, like I just told you, there's only 13 wind farms in the UK, and 2 of which are off our west coast, and there's only actually 90 megawatts of power outputted from the Barrow wind farm. So to meet a need like the 34,000 megawatts, you'll need so many more wind farms. The truth is, there is not enough wind turbines. Another reason, which is kind of related, is the fact that even if there was enough wind turbines, they might not all be working all the time. Why? May not be windy, but even if it was windy, if the wind is too much or too little, it won't work. So wind turbines will not work if there is too weak or too strong winds. Strong and too weak winds will not make the wind turbines work. Okay, that should get us the 2 marks. In fact, this gets us a mark, this gets us a mark. This is just a bit extra, if that's the way your brain is thinking. For question 1.3, some of the energy from the wind used to rotate the wind turbine is wasted. As soon as you hear the word wasted, you have to think efficiency. Wasted energy, always talking about efficiency. An engineer oils the mechanical parts. So it's like putting oil on your chain. What does it do? It reduces friction. Okay, so the question actually asks, explain how oiling would affect the efficiency of the wind turbine. Because they are asking about the efficiency, let's recall the efficiency equation. Efficiency is equal to useful energy outputted divided by total energy inputted. Total energy in. Now, this equation is used to formulate our answer. This is not our answer. Let's formulate our answer. The first thing we need to say is, if there's oil put on the wind turbine mechanical parts, the useful energy out would increase. So efficiency will increase because useful energy out will increase, and this is all because oil reduces friction. And that is enough to get us first, second and third mark. So 3 mark, it's actually a dead easy question. Next one. In most homes in the UK, there are many different electrical devices. You will be looking at this video on an electrical device. Your job is to explain why people should be encouraged to use energy efficient, all right, electrical devices. So there's only one reason why people should use energy efficient electrical devices, because less energy is used by more efficient devices. So less energy is used. So if less energy is used, there is less energy demand. You could say because there's less energy demand, you're paying less for your electricity. But this question sort of frames it in a way that it's asking you to say it reduces environmental impact. Due to electricity production. Electricity generation. We don't produce it, electricity, we generate it. That brings us to the end of question 1, and let's be honest, it's really, really easy. Welcome back. Figure 2 shows a rock found by a student on a beach. To help identify the rock, the student took measurements, and it's asking you to describe a method for the student to calculate the density of the rock. The first thing to remember is what density is. Density is mass divided by volume, or mass per unit volume. How big something is and how heavy something is divided by each of them. So the two measurements that we need to take are mass and volume. Mass is quite easy. You can just measure it using a mass balance. But the volume is a little bit tricky. If you had a regular object, you would just measure the sides and do a calculation to find the volume. Unfortunately, for an irregular object like a rock, we have to use something known as the Eureka can method, or the displacement can method, to find its density. So the first thing to do is let them know how to measure mass. So you measure using a mass balance. And for something so as small as this, it's probably going to be measured in grams. Second thing to do is let them know how to measure volume.
displacement can, or a Eureka can. Okay, so how do we do that? Well, for those of you who don't know, a Eureka can sort of looks like this. It is a can that you can fill up to the spout with water. And then what you can do is you can lower your piece of rock into the water, and when you do that, the amount of water displaced, or that comes out because it will spill over, is the amount or the volume of the rock. So what you have to do is you just have to then collect the water that is displaced inside a measuring cylinder, and the volume of the water displaced is the volume of the rock. So let's write that method. Fill Eureka can with water. Eureka can with water up to spout. And then you'll lower rock in using a string until it's fully submerged. Why do we use a string? So that only your rock is displaced in the water. If I use my fingers, I might get some fingers into the water, and then the volume actually calculated will be of the rock and my fingers together. Then what you got to do is collect displaced water in a measuring cylinder and measure the volume of the displaced water. And the next thing to say, and this is really important, so I'm going to do it in a different color. Volume of water displaced equals volume of rock. And you really have to say this to get any of those marks. And finally, the last thing, we've already done it up there, but the last thing to say is density is equal to mass divided by volume. The volume of the rock can be measured in milliliters, and then 1 milliliter is equal to 1 centimeters cubed. So really you can write your density as grams per centimeters cubed or kilograms per meters cubed. So that's how to do that. This next question says the student determined the density of the rock to be 2.55 plus or minus 0.1 grams per centimeters cubed. This symbol, if you haven't come across it before, literally means plus or minus. It's telling you there is a bit of an uncertainty on the student's result. It could be 2.55 plus 0.1, or it could be 2.55 minus 0.1, or anything in the middle, including 2.55. So there is this range of values that it could be, and you got to work out what is the top of the range, what is the bottom of the range. The top of the range is 2.55 plus 0.1, which is 2.65. And the bottom of the range is 2.55 minus 0.1, which is 2.45. And that's our answer. And then now the table gives the density of 5 different types of rock. The type of rock: basalt, chalk, flint, sandstone, and slate. And the densities with their uncertainties given. So there is a range of results that their densities could be. Now the reason why that is because not every piece of rock is the same. It's not of the same purity, and it's basically not lab grown, is it? So it has it might have pores inside it, but generally speaking, basalt is around 2.9 grams per centimeters cubed, give or take 0.1 grams. And that's what this table is telling us. Which 2 types of rock, table 1, could be the type of rock that the student had? So remember, the student had something that was in between 2.45 all the way up to 2.65. That's the range of result that they could have. Now we just got to find which two of these rocks fit in that range. Basalt is going to be 2.9 minus 0.1, which is 2.8, up to 3.0. Chalk is going to be 2.35 minus 0.15, which is 2.2, up to 2.5, if I'm correct. Yep. And flint is going to be 2.6 minus 0.1, which is 2.5, up to 2.7. Sandstone is going to be 2.0 up to 2.4, and slate is going to be 2.7 up to 3.1. Okay, so these are the ranges that our rocks lie in. Now, which one could fit this rock? Well, this one couldn't. It's out of the range. This one could, definitely in the range. 2.5 happens to be in between 2.45 and 2.65. This one definitely could. It's within the range. 2.5 happens to be in between those ranges. 2.4 is not, and this is definitely not. So you've got chalk and flint. So that's our answer. Easy peasy. 2.4 says the student only took one set of measurements to determine the density of the rock. Explain why taking measurements more than once may improve the accuracy of the density value. It already tells you that accuracy can be improved by taking multiple measurements. Why? We can calculate a mean. Alright, taking multiple readings, add it all together, divide by the number of readings that you have, and a mean value will be better than just your one value. And it also reduces the effect of random errors. Random errors are errors in maybe measuring. Maybe your scale was off the first time, and then when you zeroed it the second time and the third time, it gave you the accurate result. Or maybe there was a mismeasurement when you took the reading of the volume. Therefore, to reduce the effect of random errors, you need to do multiple readings. An engineering company has invented pavement tiles that generate electricity as people walk on them. Figure 3 shows someone walking on the pavement tiles. Use equation sheets to answer questions 3.1 and 3.2. For just a bit of context, when the tiles are compressed, the spring underneath them stores some elastic potential energy which can be released and converted into electricity. So, question 3.1 asks, what equation links current, potential difference, and power? I've got a little screenshot of the equation sheet on the right, and here are all the equations that sort of talk about power. And in these equations, the one that we want is this one right here, because that's the only equation that talks about power, potential difference, and current only. So what we do is just tick that answer. Moving on. When a person walks on a tile, a potential difference of 40 volts is induced across the tile. The power output of the tile is 4.4 watts. Calculate the current in the tile. Remember, we just have to use the equation that we were doing before. Let's go through Mr. Barden's 7-step method. First thing is, take the data from the question. V equals 40. P equals 4.4, and I is what we don't know. Now our formula is P equals V times I, and then we just have to plug all the numbers in.
4.4 equals 40 times by current, and then current is 4.4 divided by 40, which equals 0.11 amps. 0.11 gets you all three of those marks. The question is, what equation links efficiency, total power input, and useful power output? Here's a little extract from the equation sheet. Efficiency equals useful power output divided by total power input. Boom. Dials are used to power LED lights in the pavement. An LED light has a total power input of 4 watts. The efficiency of the LED light is 0.85. Calculate the useful power output of the LED light. All you have to do is plug these numbers into the equation that you just took out before. Remember, efficiency is 0.85 and the input is 4.0 watts. So you have 0.85, which is equal to the useful power output divided by 4. So useful power outputted is equal to 0.85, the efficiency, times by 4.0, which is the total power inputted. Trusty calculator, 0.85 times by 4 gets me an answer of 3.4. That's the answer that I'll write here. Alright. A student investigated the insulating properties of different materials. Figure 4 shows some of the equipment used by the student. What are the equipment used? They used a thermometer, they used a lid, they used a metal can with hot water inside, and that was the temperature they were measuring. They were measuring the temperature of the water inside, and they used insulation around it. And here's the method used. Wrap the insulating material around the can. Fantastic. Put a fixed volume of boiling water in the can. Why fixed? Because that's a control variable. Boiling water. What does that mean? Water at 100 degrees. Place the lid on top of the can. Why? So that any heat isn't leaving the can through the lid. Measure the time taken for the temperature to decrease by a fixed amount. What are they measuring here? They're measuring the time taken. Look at that. Measure the time taken for the temperature to decrease by a fixed amount. Are they measuring the temperature? No, they're measuring the time. So what are they going to have to use? Probably a stopwatch. Okay, repeat steps 1 to 4 using the same thickness of different insulating materials. Same thickness. So that means it's a control variable. Different insulating materials. Different insulating materials. That's what I'm changing. Alright, so that's my independent variable. So what's my independent variable? Insulating material. What's my dependent variable? Time taken for temperature to drop by a certain amount. Fantastic. Now, excuse me, that does not look like amount. That's better. Next. Okay, the student used 2 different types of thermometers to measure the temperature changes. Figure 5 shows the reading on each thermometer. Thermometer A, a classic thermometer. Thermometer B, a screen which shows a reading. What's the resolution of thermometer B? What does that word resolution mean? Right, let's not get stumped. It means the smallest increment that the equipment can measure in. So what that means is after 8.74, what's the next smallest reading that thermometer B can make? Well, it's 8.75 because it can count up in 0.1 degrees Celsius. Alright, next one. Thermometer A is more likely to be misread. Give a reason why. Why? Because you have to read it at eye level. If you're not looking at it eye level, you will misread it. Okay? You will misread it because of the viewing angles. Angles
All right, what does that mean? It's a parallax error. If you view it from the top, it might look like there's more in it. If you less in it. If you view it from the bottom, it might look like there's more in it. Okay. All right. For one type of insulating material, the temperature of the water decreased from 85 degrees to 65 degrees Celsius. The energy transferred from the water was 10.5 kilojoules. The specific heat capacity of the water was 4,200 joules per kilogram degree Celsius. What's the difference between this one and this one? This one is in kilojoules, and that's not standard units. We want that to be in joules, but we'll do that later. Calculate the mass of the water in the can and use the physics equation sheet. When we use the physics equation sheet, there's only one thing that links the change in energy, the mass, the specific heat capacity, and the change in temperature. All right, that equation is E equals mc delta theta. So we need to use this equation here. The first thing to do is write down the data. All right, so change in energy. Do we have that? Yes, we do. It's 10.5 kilojoules. To convert kilojoules to joules, I times it by 1,000, so I get 10,500 joules. Fantastic. The next piece of data that we need is mass, but we don't have that. That's what we're trying to find out. Next is specific heat capacity. Do we have that? Yes, 4,200 joules per kilogram degree Celsius. Next piece of information we need is our change in temperature. Do we have that? We do, except it's not given as change in temperature. It's given as the starting and the final. All right, so decreased from 85 to 65. What is it? 65 minus 85 gives us the answer of minus 20 degrees Celsius. So it goes down 20 degrees Celsius. We need to calculate the mass of the can. So although the change in is a negative, it goes down. We don't really need the negative. I'm just telling you that it goes down by 20 degrees Celsius. Now we need to calculate the mass of the can. Let's plug all our numbers into it. So 10,500, oops, one too many zeros, is equal to mass times 4,200 times by 20 degrees Celsius. Now 10,500 divided by 4,200 times by 20 is equal to mass. Now we just have to plug all those numbers into our calculator. And what do we get? We get an answer of mass being equal to 0.125, and that's in kilograms, and that's the answer that they want, 0.125. Well done. Right. Table 2 shows the results of two insulating materials, material X and material Y. The time for the temperature to decrease by 20 degrees is given in seconds. X, the temperature decreases in 450 seconds, but for Y, it takes 750 seconds for the temperature to decrease. It says explain how the results in table 2 can be used to compare the thermal conductivity of the two materials. Which one is a better thermal conductor? It is obviously X, because it takes less time for the temperature to decrease by the same amount. Alright, and which means the rate of energy transfer is higher. What does that mean for X? X takes the temperature from the hot water and transfers it to its surroundings at a much faster rate than Y does. So X has higher thermal conductivity because why? Because same temperature change in a shorter time. What does that mean? Rate of energy transfer is higher for X. That's what it means. Alright, energy transferred over time, rate of energy transfer. Fantastic. A student rubbed a plastic rod with a cloth. The rod became negatively charged and the cloth became positively charged. Explain why the cloth became positively charged. If we think back to what we can do with a balloon, when we take a balloon and rub it on our hair, we can stick it to the wall because of electrostatic forces. When two insulators, such as the cloth and the rod, or the balloon and the hair, is rubbed together, there is a transfer of electrons. And electrons are negatively charged. Whichever one that you take the electrons off of, that remains with more positive charges than negative charges. And that's the cloth. In this scenario, the cloth remains with more positive charges than the negative electrons that you rubbed off it. So to answer your question, you're right. Electrons are transferred from cloth to rod. That gets us 1 mark. Then remembering that electrons are negatively charged, gets us our 2nd mark. Our 3rd mark is for saying that more positive charges are left on the cloth. There we go. 3rd mark. So, figure 6 shows the negatively charged rod on a balance. There's the negatively charged rod. Here's some insulating material to stop the charge from flowing. And here's a mass balance which shows a reading of 100.25 grams. Figure 7 shows another charged rod being held stationary above the rod on the balance. So someone's holding another rod there. And remember, that rod is also charged. The rods don't touch each other. But what you notice is that the mass increases by 0.1 grams, but still increases. So explain why that reading on the mass balance increases. It's not like there isn't any explanation for it. The explanation comes from the fact that both rods are negatively charged. So here's both rods, and I'm just going to draw loads of negative charges on it. Negative, 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 negative. And if two negatively charged rods come close to each other, then there is an electrostatic repulsion that happens. Two like charges, they repel each other, they push against each other. That push against each other causes the rod that is on the mass balance to push down onto the mass balance, which is read as a difference in mass. So the question is, explain why the reading on the mass balance increases, and you say more force down on the mass balance. Where does more force come from? From the fact that the rod is negatively charged negatively charged, and like charges repel. That's it. 5.3. The balance had a zero error. The zero error is not important in this experiment. Give the reason why. A zero error is when the mass balance does not read zero to begin with. Instead, because there is something on it, it has a reading. If we tear, do you remember tear? If we press the tear button on the mass balance, then even with the first rod on there, it will say 0. Then there's no 0 error. Then whatever you do to the mass balance afterwards, like holding the rod above the other one, will be read from 0. But we don't really care whether it's read from 0 or 100.25. All we care is that there is a difference in mass being measured. MESURAD, measured. Because that's all we're looking for. 5.4. A negatively charged rod is held near an earth conductor. Question 6. Figure 8 shows how electricity is supplied to consumers by the national grid. National grid is a series of cables and pylons that take electricity from power stations to the consumers. Explain why transformer X is used in the national grid. Transformer X is a step-up transformer, and its job is to take the potential difference created by the power station and step it up to around 400,000 volts. Because it is at such a high voltage, the current is going to be really low. And the current needs to be low in the wires to avoid the wires from heating up and transferring energy to the surroundings. If it transfers lots of energy to the surroundings, the efficiency would be low. So the step-up transformer improves the efficiency. The first thing to write is X is a step-up transformer. And it increases potential difference, decreases current, and if current is low, reduces energy transfer to surroundings, and if there's less energy transferred to the surroundings, it improves efficiency. Okay, now the first bit that is not mark worthy. These 4 bullet points are the 4 bullet points that will get you all 4 of those marks. Explain why transformer Y is used in the national grid. If we go back, we'll be able to see transformer Y takes the electricity from the cables into people's homes. 400,000 volts is a lot of voltage, and it's unsafe to use in a home by consumers. So transformer Y decreases potential difference to a safe level or a safer value. Those 2 things get you the mark. If it was to a house, then the safe value is 230 volts. But if it was to a company or like an industry, that they will need more voltage, so they'll get more, like around 20,000, 40,000 volts. The town of Hornsdale in Australia has an electricity supplied by a huge battery. On one day, the battery transferred 3.24 times 10 to the 11 joules of energy to the town. That's my energy transferred. Usually has the symbol E. The potential difference of the town's electricity supply is 230 volts, just like the UK. Calculate the charge flow to the town on this day, and charge flow has the symbol Q. Well, how did I know that charge flow had the symbol Q? Because I learnt it from the symbols test. Use the equation sheet to give your answer to 3 sig figs. First thing is extract the data. I've already done it. Normally I wouldn't write this step out, but just for you, I'm going to. E equals 3.24 times 10 to the 11 joules. And then my V, potential difference, equals 230 volts. And my Q is what I'm going to try and find out. Next, go to the equation sheet and find what links energy transferred, potential difference, and charge flow. And the equation is E equals Q times V. Now, at this point, I just have to plug the numbers in. But there is something that I have to address, and that is this standard form. If you don't know what standard form is, pity on you, but I'm going to tell you anyway. 3.24 times 10 to the 11 means 3.24 times by 10 11 times, or taking this decimal place, moving it to the right 11 times, which gives you the number 324,000,000,000. Let me just check if that's correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Perfect. That's the right number. So let me plug that number in. 324,000,000,000,000 is equal to Q times by potential difference 230. Now, why would I normally not bother with this? Well, it's because you can plug standard forms into your calculator. You can just type in the times 10 to the button, which is normally at the bottom, and type in times 11, and that number is perfectly fine. Alright, so now we do a bit of rearranging of the equation to make Q equal to that number. You know I'm not enjoying writing this out. This is why standard form is really, really good. Divided by 230, which gives you an answer of 140,8 695 652. I'm not a genius. I just have a paper with the answer written on. I just have to make sure I copy it correctly. 140,869,5652. Awesome. Now, what do we have to do is, we've done this, we need to give our answer to 3 sig figs. This is where I made the mistake of just rounding it straight away. To give it to 3 sig figs, I go, that's my first significant figure, that's my second significant figure, and my third significant figure happens to be a 0, and I'm just going to round this 8 up to a 1. It gets me an answer of 141,000,000,000. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that makes more sense. Now, that is the right answer, and I can just write that on my answer line, and it would be correct. However, just for the people who have been doing it properly, I need to give it in standard form, don't I? 1, 4, 1, and standard form always starts with an integer, decimal, and then whatever numbers that follow 1, times by 10 to the power of 9, because I have to go 1, 2, 3, 4, 5, 6, 7, 8, 9 times to get back to this answer. 4 marks. Actually not that much effort if you understand your standard form. If you don't understand your standard form, it's very difficult. Next question. Alpha particles, beta particles, and gamma rays are types of nuclear radiation. What does the alpha particle consist of? Fantastic question. The alpha particle is always the helium nucleus. Alright, and the helium nucleus, if we can do PEN, on that has 2 protons. Electrons, I don't care about, but it does have 2. I'm just going to put a cross through it. And neutrons, it has 2. So realistically, if I were to do this, protons like that, and my neutrons like this, my alpha particle will have 2 protons and 2 neutrons. Now, none of this what I've just done, you don't have to write. You don't have to write any of this down. All you have to write down is that it has 2 protons plus 2 neutrons. That gets you the 1 mark. Next mark. A krypton nucleus decays into a rubidium nucleus by emitting a beta particle. Complete the nuclear equation for this decay by writing the missing number in each box. They have been super generous with you because they have told you what that beta particle is. It is a fast-moving electron, therefore it does not have a mass. It has a charge of -1, which means that its bottom number or its atomic number is -1. That is just for simplicity. What does that actually mean? It means this side of the arrow and this side of the arrow have to balance each other out. The top row and the bottom row have to balance each other out. So this number, whatever it is, has to be 85 plus 0. 85 plus 0 is 85. That's 1 mark. This number, whatever it is, has to be, this number plus as -1 has to equal 36. So 36 equals something -1. What is that something? It's 37. That's it. Easiest 2 marks in your paper. Internal contamination of the human body means radioactive material is inside the human body. Explain how the risk of internal contamination is different to the risk from external irradiation by a source of alpha radiation. Lots to unpack here. So it tells you what internal contamination versus external irradiation is. Well, internal contamination means radioactive material is inside. Alright? That's really important. Explain how the risk from internal contamination is different to the risk from external irradiation. External irradiation means the source is outside and only the radiation is sort of coming towards you. The main thing to remember is we're talking about an alpha source. And alpha sources have a very short range in air. So that means if there was a alpha radiation source at the end of this pen, I'm safe where I am because few centimeters in air is as much as it can travel. But say it was right next to my hand, what would happen then? Well, my skin is enough of a barrier to stop the alpha radiation. Alpha particles are not penetrating, they are really weakly penetrating. That's the first thing that I'm going to write. Alpha particles have a low penetration ability. Yeah, that's how it's spelled. It can't get past skin. So what I'm going to write is it is stopped by skin from external radiation. Alright, so oops, that's not what I meant to write. I meant to write irradiation. IRRADIT, irradiation. So external irradiation is stopped by my skin. But what if it actually went inside me? What if I swallowed a piece of material that was an alpha source? Well, then it's really dangerous because alpha radiation is absorbed by living tissue. Alright, it's dangerous because the cells, my cells inside me, will absorb the alpha radiation that is right next to it. And it's dangerous because alpha radiation is very highly ionizing, which means it can knock electrons off particles. And because it's highly ionizing, it can cause harm to cells and increase the risk of cancer. So the next thing that I write is alpha radiation is highly ionizing and can cause harm to cells and increase the risk of cancer. Why does it increase the risk of cancer? Because it can cause mutations in cells. That's it. Because it knocks the DNA and sort of alters it and cause mutations which can cause cancer. A lot of information there. And if you say these two things and these three things, you will get all your 5 marks. Here is where this comparison sort of mark comes in. Or sorry, 4 marks even. These two things and these two things will get you 4 marks. But the comparison mark comes in by saying is contamination or internal contamination is more dangerous. Of course it is. Because externally it's stopped by the skin. Next question. A student determined the specific latent heat of vaporization of water. What does that mean? Think about it. Alright, so they used a power supply, they've connected some wires, here's a heater, there's a water, there's the beaker. Here's how they've done it. They put 50 centimeters of cubed of water in the beaker, they measure the mass of the beaker and the water, they use a heater to boil the water and keep it boiling for 600 seconds, measure the mass of the beaker after the 600 seconds, and what measuring instrument should be used to measure the volume of the water. They've told you all this information. They've asked you a really easy question first. What do I use to measure the volume of anything? Volume is measured in centimeters cubed or milliliters. And to measure volume of water, you use a measuring cylinder. Make sure you spell it right because it's only 1 mark. You might as well spell it right. Next one. What is the hazard in the student's investigation? Or hazard, what does that mean? It means something that could cause something to go wrong. Summit? That's rubbish. Something that could cause something to go wrong. Now, burns is something going wrong. Boiling water could cause something to go wrong. So that is my hazard. Heat-proof gloves, that is safety equipment that I'm wearing. Safety goggles, again, safety equipment that I'm wearing. Boiling water is the hazard. If I don't take enough precaution, the boiling water could cause burns and the risk is the burn. Next one. 8.3. The initial mass of the beaker and water was 0.8 kilograms. The final mass of the beaker and the water is 0.71 kilograms. The energy transferred by the immersion heater as the water boiled was 25,200 joules. Calculate the specific latent heat of vaporization of water given by the student's data. Give the unit. Use the physics equation sheet. It's a big question. But it all starts by understanding what specific latent heat of vaporization is. The specific latent heat of vaporization is the energy needed to change 1 kilogram of water from liquid to gas. The energy needed to change the state of 1 kilogram of water, but it has to be at constant temperature. So if you think about it, it's not the energy that you put in to get it to 100 degrees. When at 100 degrees, when it's boiling, The energy that you put in then, that is the latent heat of vaporization. Because the energy is not going in to heat it up anymore. Because if you think about boiling water, it doesn't go to 101 degrees. It stays at 100 degrees. Because after 100 degrees, the water will turn into steam. That's what's happened here as well. In the beaker, you had some water, and after boiling it for 600 seconds, you had a little bit less water. So the energy that went in at that point went in to change that much water into steam. We want to know how much energy that is for 1 kilogram. How much, if I had to change 1 kilogram of water into steam, how much energy would I have to use? Complicated question, but easy because it's maths. Right, so first things first, let's find what equation I need to use for specific latent heat of vaporization. The equation that I need to use is E equals m times L, where L is the specific latent heat of vaporization and m is the mass, but in this case how much mass you change. So I'm going to say change in mass, and energy is the energy that you put in. Therefore, E is equal to 25200 joules. M is equal to 0.08 minus 0.071, which is 0.009. Yeah, that's right, 0.009. So that's my mass that I've got. Now I need to find my L. E, just plug the numbers in. 25200 is equal to 0.009 times by L. L is 25200 divided by 0.009, which gives you an answer of, I've done it here already, 2800000 joules per kilogram, because I'm dividing energy by mass. And in standard units, that happens to be 2.8 times 10 to the 6 joules per kilogram. Whenever I'm doing units, I'm just looking at what are the two numbers that I times together, or what are the two numbers that I divide together, and I'm always putting that. But you should know that the latent heat has joules per kilogram as its units, because you'll have done the units test and you'll have memorized it. Superb.
Some thermal energy was transferred to the surroundings while the water was being heated. Explain how this affected the student's value for the specific latent heat of vaporization of water. If some energy was transferred to the surroundings, that energy was not transferred to the water. And we assumed that 25,200 joules of energy was transferred to the water. And if that value is too high, then the latent heat of vaporization that we calculated was also too high. So we say less than 25,200 joules of energy. Energy does not need a capital letter. Was transferred to the water. Okay. So value L was too high. Good job. 8.5. Some of the water evaporated before its temperature reached 100 degrees Celsius. Explain how this affected the streaming value of the specific latent heat of vaporization of water. We assumed that the energy going in was to boil or vaporize the water at 100 degrees. If some of the water evaporated before it reached 100 degrees, that's when we started measuring, by the way, then our value that we got for mass change was too high. If the value that we got for mass change was too high, then actually our latent heat of vaporization value that we calculated was too low. So what we say is measured change in mass was too high. So the student's value for F is too low. What a question. It asks you about latent heat of vaporization in every way possible. Next one. Question number 9. Figure 10 shows a girl doing an experiment to determine her power output by running to the top of some stairs. How very exciting. The mass of a girl is 60 kilograms. The height of the stairs was 75 centimeters and 175 centimeters. The girl ran to the top of the stairs in 1.4 seconds. Gravitational field strength was 9.8 newtons per kilogram. Calculate the power output of the girl. They give you lots of information, but they don't actually tell you how to calculate the power output. They say use the equation sheet. So the first thing to do is write down all the information that we know. So mass is equal to 60, height kilograms, height is equal to 175 centimeters. Immediately we know that's not in the standard unit, so we can change it to 1.75 meters. 100 dividing by 100, obviously 100 centimeters in a meter. Then we know that our time is 1.4 seconds, and we know our gravitational field strength is 9.8 newtons per kilogram. The first thing to do is write down the equations that we might need. For power output, the equation generally is energy transferred divided by time. In this case, the energy transferred, well, from the bottom of the stairs to the top of the stairs, the energy transferred is gravitational potential energy, so we need to write down that equation, which is m times g times h. This is the first equation that we use, is mass, we might as well substitute straight away, 60 times by 9.8 times by 1.75. If we do all that, we get an answer of 10 to 1029, and that's in joules. Fantastic. Now that we know how much energy is transferred, we can substitute that number into our power equation. Power output is 10,029 divided by the time taken, which is 1.4 seconds, which equals, and I've already done this on a piece of paper, 735 watts. Fantastic. That should get you 5 marks. Now, 9.2, the total power output of the girl was greater than the answer to question 9.1. Why? Well, not only does the girl's gravitational potential energy increase, but because she's moving, her kinetic energy increases as well. Girl's kinetic energy increases as well as GPE. So we only calculated the power output for GPE, but actually her kinetic energy increases as well. And we could calculate that with a little bit more information. Some energy will be wasted. How is it wasted? Well, her muscles need to do some work, so in thermal energy, it's wasted. Shoes will be making some noise and stuff like that. It won't be a perfect 100% efficient energy transfer. Okay. Question 9.3 says a boy took more than 1.4 seconds to run up the stairs. So here's the stairs again. Okay. The power output of the boy was the same as the power output of the girl. So power output is the same, but he took more than 1.4. So energy transferred, we'll leave that there. I'm going to say this is, I don't know, more than 1.4. Let's say it's 2 seconds. Right? So if they took more time and the power output was the same, then that means the energy transferred must be more. All right, more energy transferred in more time. All right, so the power output has to be the same. How can he transfer more energy than the girl? Well, it's not that complicated because the way he can transfer more energy than the girl is if he was more massive. Oops, stop working a bit. There you go, if he was more massive. Next one, question 10. Figure 11 shows a student launching a toy airplane. To launch the airplane, the student pulls on it to stretch the spring and release it. So when you stretch the spring, the elastic potential energy is stored, and the toy airplane is then fired. I used to have a toy like this. Just before the toy airplane is released, the spring has an extension of 0.12 meters, and the mass of the airplane is 0.02 kilograms, and the spring constant is 50 newton meters. Calculate the maximum speed the airplane is at just after it's launched. All right, so this is the energy that's going into the airplane, and to calculate the speed, we need to know the kinetic energy the airplane has. Well, if this is 100% efficient energy transfer, the kinetic energy the airplane has is going to be the same as the elastic potential energy that the spring is loaded with. So let's find the elastic potential energy first. I'm not going to bother writing down all of the values for this question. I'm not going to extract all the data because it's all here. So let's start with the equation sheet and finding the equation. The equation that we need for elastic potential energy is half k E squared. Now E is the extension and K is the spring constant. All right, so let's find out the energy transferred is 0.5, which is half, times by 50 times by E squared is 0.12 squared, which gives us an answer of 0.36 joules. That's awesome. Now, 0.36 joules is how much energy is transferred by the spring. That is the energy that's gained by the airplane also. So I'm going to have a next equation that we need, and we'll do it in a different color just to make sure it's visible. EK is half mv squared. Our mass is here, and our velocity squared, well, that's what we're trying to find out. So EK happens to be the same value as this, so 0.36 is equal to 0.5, which is half, times by mass, which is 0.02, times by velocity squared. When we do that, we get velocity squared is equal to 0.36 divided by 0.5 times 0.02, which gives us an answer of 36. V squared equals 36, so V equals square root of 36, which is 6. Speed is 6. Speed is measured in meters per second, and that is 6 marks. How easy is that? Next question. Complete the sentence. As the aeroplane moves upwards through the air, there is a decrease in what energy? As it's moving upwards, it's colliding with particles of air. It's not decreasing in its gravitational potential energy because it's increasing in its gravitational potential energy. The energy stored that decreases is its kinetic energy because it's going to slow down. So kinetic energy. I like the other colour better. Give one factor which would increase the distance the toy airplane travels horizontally before hitting the ground. This is not a tricky question. It's not actually asking you any physics. It's asking you what would make the toy airplane go further. Well, if I stretch the spring more, that's all you have to say. More extension in the spring. If there was more extension in the spring, there will be more elastic potential energy. Elastic potential energy, that's how I'm going to leave it. Next question, question number 11, last question for us. It is figure 12 shows some hair straighteners. The hair straighteners contain heating elements. When the hair straighteners reach normal operating temperature, an LED turns on. Draw the circuit diagram for an LED in the box. Let's get this perfect. with a diode. By the way, an LED stands for light emitting diode. And so that's a diode. And then to show that it's emitting light, you put a circle around it and then you draw two arrows. That's it. Next one. Figure 13 shows a circuit diagram for the hair straighteners. Each resistor represents a heating element, okay? And the power output of the hair straighteners can be changed by closing different switches. Why do the hair straighteners not turn on when only switch S2 is closed? Fantastic questions, because switch S2 being closed does not provide a conducting pathway for the electrons to flow from the power supply. So what I would say is switch S1 needs to be closed to complete the circuit. Okay, next question. The hair straighteners have a maximum power output of 120 watts. That's my power. The energy transferred to the hair straighteners reach normal operating temperature. The energy transferred to the hair straighteners to reach normal operating temperature is 3.6 kilojoules. Kilojoules I will automatically convert to 3,600 joules because kilo is 1,000. Okay. Calculate the time taken for the hair straighteners to reach the normal operating temperature when operating at maximum power. Calculate the time taken for the hair straighteners. So we're asked to calculate. I'm going to do it in a different color here, or a different red. We're asked to calculate time for the hair straighteners to reach normal operating temperature when operating at a maximum power. You have to use your physics equation sheet. We don't really have to, because we've come across this equation before, even in this exam. And the equation is power is equal to energy transferred over time taken. All right, we've got the power 120. We've got the energy transferred 3,600. We do not have the time taken. Okay, so to do that, T equals 3,600 divided by 120, which equals 30 seconds. That's it. Last question. Figure 14 shows the hair straighteners circuit with switch S1 closed. Okay, switch S2 and S3 are closed at the same time. Explain what happens to the power output of the supply. This is a good question, because going this way, when only switch S1 is closed, that's the resistance of the circuit. When switch S2 is closed, there is two more branches. When S2 and S3 are closed, there's two more branches for the electrons to flow. If there's more branches for the electrons to flow, then there is less resistance, or total. I'm going to rewrite that. Less total resistance for the circuit. If there's less total resistance for the circuit, then there's more current. All right, so more current. Not more current here or here or here, more current overall here in this section of the circuit. Okay, so there's more current, and if there's more current, remember, power is equal to current times potential difference. So same potential difference, more current, so more power output. 3 marks, jolly good.